First of all, I thank you for the World Innovation for Innovation Techs and Expo. Myself is Dr. M. Premkumar in Department of Mathematics in Satyabama Institute of Science and Technology in India. Next, I thank my guide, Dr. E.G. Rajan. Today, our topic is Geovision 3D, a high throughput, the three-dimensional image understanding system for the geomatics professionals. So high cost drilling for the problem identified. The drilling is usually done by the service company and drilling contractor. The drilling company is operates in accordance with the contract, which is specific that the drilled will be the specific depth. The contractor is paid on per day for the foot drilling rate. In this year 2007, the 4 million drill and oil well and 3.9 million to drill the natural gas well. The average cost of the drill as well as the 574 million of the depth. The average cost of the find that develop the oil and the gas, the property United States, the 17.01 million, the barrels of the oil equivalent. So the based upon of the statistics of the one out of the 5 rigs, the drill area held from the oil recovery. So how to reduce the high drilling cost? It is the not worth for drilling the all possibilities of reducing the cost of located oil well, the 4 million and to the 16 million. There is the presentation I aim to for showing this such a possibility. The aerial survey for the locating potential area for the prospecting oil field. So the three-dimensional digital image processing is an important area of research that has been the numerous application in the field of medical imaging, the seismology, and geomorphology, and remote sensing and material sciences. Depending on the requirement for solving the specific problem, one has to identify various features of the three-dimensional images while applying the suitable algorithms. For example, the quantitative analysis of the geomorphological structures in GPR, the radargrams, and other similar images require extension of the volumes and shapes and geological the constructs like oil reserves, the ores and minerals and encapsulated the gems and gold and diamonds present the below earth surface. In order to this, the need to the aerial survey of the area interest for the locating the land of the scanning use the ground penetrating radar. So the area of the here we see this, the aerial survey of the locating the potential area for the prospecting oil field. This is the desert, is on trees and the camel is there just walking this. The how true contractors are drilled to oil and gas, it is necessary to drill, obtain the crude oil and natural gas from the under the earth surface. The engineers makes the hole using the rotary drilling rig. Here we see this, we propose the state of art the project Geovision 3D for subsurface image acquisition and analysis. The major objectives of the project to develop the new methodologies for the data acquisition or processing and interpretation, to integrate the multiple technologies focusing the vertical seismic profiling methodology and interpretation, the great discovery of the new oil resource, the oil field of development and management for the maximum economic oil recovery, to make us use the vertical seismic profile methodology for prospecting minefield development and management for the maximum economic recovery of various minerals and gems. Then the other subjects of the project to devise the methodologies for the collecting data from underground of the earth crust, the data acquisition sensors like synthetic aperture of the radar and ground penetrating radar and the microwave pulse, the transmitters could be used in achieve this. The other seismographic techniques could be also used alternatively association in ground penetrating radar. The multiple sensors, the fusion is the next part. The data collected from various sensors could be the integrated at the data set from which is the quite a lot of information about the subsurface elements could be interpreted. Then fast and reliable algorithm for extracting the information from the data set, the major R&D component of involved in the project. To develop the artificial intelligence based on the expert system software package and the integrated component with the given geodata processing requirement, the minor civil engineers and archaeologists would be the find out the package of the very useful. To develop a state of the art, the technology used to abort tools of the detecting oil and minerals and the gems, the research in the particular area from which is the genuine and the reliable data set and be collected. As the part of this project, the few people would be that find the state of the art operational methodology of oil exploration. Here we see this, the methodology to be used, the field model, the rectangular and hexagonal. Let us consider the main field model, the shown here the rectangular in first figure and the hexagonal of the second figure. The rectangular model is generally the prepared to avoid the operational difficulties. The rectangular model will be the divided into the matrix in 11 cross 9 sub-regions. Here we see this, the scanning patterns of the prospecting the minefield. The scanning of the minefield field carried out the using the GPS controlled autonomous mobile robot. The system consisting of the ground penetrating radar and image acquisition system. Note that the serpentine scanning is used to the prospecting the minefields. The first one is the raster scanning and second one is the serpentine scanning. The major of this project, the autonomous mobile robot for the scanning of the field. The proposed the AMR would be the consist of the ground penetrating radar and global positioning system, the control and guidance system, and communication system and power supply, the vision system and chassis. So they are moving to this the autonomous mobile robot in GPR and control system. Just move on side. You see this picture. The hypothetical existence of the points with the pink point will be the echo of this the model of the echo from the point of the existence is to start from this the scanning over the received the signal in the analog from the ends it should be the covered to the desired form. Here we see there is a data acquisition. The sampling of the analog signal is carried out to the Nyquist frequency without the causing any loss in the vital information related to the characteristic. The echo due to the various surface images. The first one is the model of this echo from the point of existence. The second one is the sampling of the analog waveform. Here we see this, the ensemble of one-dimensional signals as assumed for the hypothetical minefield model. In top of this figure, the surface of this subsample field, the in between is the one-dimensional data from the subsample area. Then the last one is the bottom of the figure in subsurface at a desired depth. Then another one is this, the solid three-dimensional model obtained by the dilating these spatially distributed ensemble of one-dimensional signals is the surface of the subsample field in top of the bottom. In three-dimensional image, the data model obtained from the sampled data set in between gaps in subsurface at their desired depth. This is the solid of the three-dimensional model is called the vertical seismic profile stock. So here we see this, the elevation and right side full section wave of the vertical seismic profile stock, the subsample field and the full section wave of the three-dimensional image data profile, and the bottom of this, the subsurface at the desired depth, is the another one picture, the subsurface of the subsample field and the full section wave of the three-dimensional image and data profile. In right side wave, this one is the elevation, then subsurface at your desired depth. Here we see this, the vertical seismic profile and horizontal seismic profile stocks. The first figure one is the vertical seismic profile. The vertical seismic profile refers to this is known as the sectional profile. The horizontal seismic profile is known as the depth slices or time slices. The vertical seismic profile stocks is generally used to predict oil and other minerals of the resource, where the horizontal seismic profile used to be the archaeological survey. So here we see this, the real-time example of the depth slices obtained from using the GPR. The individual lines of GPR data represented the sectional wave of this surface. The multiple lines of the data systematically collected over an area be used to construct the three-dimensional images. The data may be presented the three-dimensional blocks or horizontal, vertical or slices. The horizontal slices as essentially plan to wave the maps of the isolating specific depths. The time slicing of the become the standard practice in archaeological applications. They become the horizontal pattern obtain the most important indicator of the cultural activities. So here we see this, the image of the subsurface depth slices is sensed by the ground penetrating radar. The first figure is the scanning this. So they executed the site. This is the moat. They exploded the wave of the moat. So there is a measure of this project. The two phase of this project. The phase number one, the prediction of unknown data from known 3D radargram. The phase number two, subsurface truth evaluation. The phase number one, here we see this in data interpolation. For example, consider the land area from 1 hectare, which is the equivalent to 1000 square meters, is the 1 hectare of land divided into 100 subregions. The second picture is the 100 meters, and the third one is the 10 meters. Is the basic problem addressed in the phase number one of the project. It is sufficient to have 1 million data samples from prospecting the 1 million cubic meters of the surface earth volume at the rate of the 1 pixel for 1 cubic meter of the subsurface earth volume. Alternatively, the one wishes to have the final resolution of 8 million data samples for prospecting, 1 million of cubic meters of the subsurface earth volume at the rate of the 1 pixel for the 50 into 50 into 50 cubic centimeters, that is the 0.125 cubic meters of the subsurface earth volume. Then the radargram would be the size of 200 into 200 into 200. The question that we arise, this given radargram sizes 100 into 100 into 100, it be the possible to obtain the radargram of the sizes 200 into 200 into 200 with the better resolution. This the question of the answer is the phase number one. This project is developing the intelligent algorithm for predicting of interpolating the data set required using the traditional GPR equipment of the real-time situations. Here we see this, the solution of this problem. What do we use this? The indigenous methodology of three-dimensional morphological dilation using a non-linear predictor. This predictor is being tested for the robustness and speed. The algorithm forms the core of this phase one project. The first one image is the measured data sample and the empty space. This is this. The measured data sample and predicated the data sample. The proof of the concept, the skeletonized version for the two-dimensional image, and it is the reconstruction. The first image is the sample two-dimensional images and skeletonized two-dimensional images, and the third one is the morphologically dilated two-dimensional images. The skeletonization is carried out on the sample two-dimensional image using an indigenous algorithm. Note that the one cannot reconstruct the original two-dimensional image from the skeleton because much information is lost in the process of skeletonizing. The figure on this right shows the approximately reconstructed 2D dimensional image from the skeleton. The two-dimensional morphological dilation is used here with the help of the specific structuring element. Note that the dilation has been carried out without the help of the prediction or interpolation algorithms. The proof of the concept, subsample version of a two-dimensional image, and it is the reconstruction. The first image is the sample two-dimensional image. The second one is the subsample two-dimensional image. The third one is the morphologically processed two-dimensional image. The subsampling is carried out the sample two-dimensional image using an indigenous algorithm. Note that the one cannot reconstruct the original image, two-dimensional image from the subsampled in two-dimensional image because 75% of the original information is lost in the process of the subsampling. This figure one right shows the approximately reconstructed two-dimensional image from the subsampled two-dimensional image. The two-dimensional morphological dilation is used here with the help of the specific structuring element. So note that the dilation has been carried out without the help of the prediction of the algorithm. The proof of the concept, subsampling of a three-dimensional image and reconstruction is the sample three-dimensional images, the subsample three-dimensional images, and third one is the reconstructed three-dimensional images. The sampling same procedure in carried out the sample of the three-dimensional images using the indigenous algorithm. Note that the one of the cannot reconstruct the original three-dimensional images from subsample from the 50% original information is lost in the process of the subsampling. This figure, the right extreme shows the reconstructed the three-dimensional images from the subsampled three-dimensional images. The three-dimensional morphological dilation is used with the help of the specific structuring element. Note that the dilation has been carried out without the help of the interpolation algorithm. The proof of the concept, the skeletonized version of the three-dimensional image, and it is the reconstruction. The sample of three-dimensional images and the skeletonized three-dimensional image one wave and skeletonized three-dimensional image another wave. And the fourth one is skeletonized three-dimensional image yet another wave. And the fourth one is the reconstructed three-dimensional image. The skeletonizing is carried out of the sample three-dimensional image using indigenous algorithm. Note that the one of the cannot reconstruct the original three-dimensional image from the skeletonized the three-dimensional image because the more than 50% of original information is the lost in this process of skeletonization. The figure on the right extreme shows the reconstruct the three-dimensional image from the skeletonized three-dimensional image. The three-dimensional morphological dilation is used here with the help of the specific structuring element. Note that the dilation has been carried out without the help of the interpolation algorithm. So this is the proof of the concept, the interpolation of the 3D radargram, the slice of the better resolution. The first one is the two-dimensional sectional slice of the 3D radargram. The subsample images of 50% losses is introduced. The highlight images using 5x5 structuring element. The last one is the reconstructed the 3D radargram slices. This is the one of the screenshot videos of the Geovision 3D operations in 3D radargram slices. The image, the radargram loaded. The image is spread, the 75% loss is introduced. Is the image also is 5x5 structuring element in labeled. The dilated image is enrolled with the 3x3 structuring element in labeled. This operation is called the morphological filtering. The idea is began the filtering as a 75% information loss and the loss of information required to the morphological filtering. This the operation is analog the interpolation data radargram that the size of integration the radargram of this that becomes the 2W and 2H into 2D. So the here we see this the pattern recognition in the 3D radargram. The page number 2, this the 3D radargram shown is obtained using the ground penetrating radar. Is the detail actual the site the surveyed of the unknown. The technical details will be the operation of a ground penetrating radar uses the surveying but the found of the literature. The 3D radargram shown is consist of the 81 the vertical seismic profiles. The stacked one behind the other. The 6 of the 81 vertical seismic profiles is shown here. The purpose of the understanding this the 3D radargram constructed the vertical seismic profile types. The first slide and this is the second one and this is the third and this is the fourth and fifth and sixth. The 3D radargram has been the process of the subsurface truth elevation of the very valuable state of this art technique, the prospective the minefields and high degree of the precision and reliability. Is the process of the 3D radargram. A complex 3D images, the processing of technique has been used to extract the finer content of the 3D radargram. The number of filtering the operation where the carried out the original three-dimensional radargram shown in the previous slide is the result is obtained shown is here. The type of the filters, the way of this 3D radargram will not remain the same for any other given radargram. However, the one can be used the set of filters identify this purpose. The 8 of the 81 sectional slices of the process the radargram are shown here. The purpose of the understanding in the ground truth evaluation will be the 3D radargram. So this is the demonstration.
I'm loading the 3D radargram. It's loaded here on the left hand side, window, just rotating it. Now I'm processing this. You see this is no information we can obtain from this diagram. What I'm doing is I'm processing the stored picture. You see this errors multiple operation has been carried out on this. Now I'm working on this particular image. I'm trying to find out the edges, 3D edges with a threshold 10. Execute. It's 2 seconds. It took 4.7 seconds. And that is the picture. I'm just rotating this. You can see this. It's not clear. What I'm trying to do is now I'm going to increase the voxel intensity. Reload this picture first here on the left hand side. So here, edges. The same picture has been reloaded here now. What I'm doing is I'm just multiplying this voxel wise, I'm multiplying by a value 3. Execute it. And that is the picture. I'm trying to zoom in. I can see the zoomed picture. See the image. Everything out. Now I'm trying to rotate it in all possible directions. See a clear view of this, what it's all about actually. Okay, huh? So because of the image of the 3D radiogram.
Next see this, the architecture of Geovision 3D. The Geovision 3D, the oil and minerals and gems and diamonds and gold, the rare elements of this, the architecture of the Geovision 3D. So the concluding of these remarks, the Geovision 3D would be the powerful tool visualize and process of the 3D radargram images. The vertical seismic files, the obtained using the scanners could be the visualized and processed with the high degree of the reliability. The many unique of the significant features of this not available in the most other software packages. The three-dimensional technology used in the development of the technically in superior to the most other available technology. And speed and precision and reliability at the far above this, they exhibited by the most other software packages. Then comprehensive packaging and developed using the in-house theoretical concept and paradigm tools. The electronic discussion could be performed with the help of the software associated in hardware. The technological bond to the geometric professionals and civil engineers. The very high social and commercial impact is anticipated. The concluding of these remarks in the commercial and social impact, the commercial advantages, a multi-million-dollar business in anticipated once the global market in probably identified. The mining engineer, the archaeologist, and even individual can afford to purchase the Geovision 3D. The social impact, the 3D three-dimensional technology used in the developing this package that could be also be used in the developing software for the medical imaging and